So, hello everyone, welcome to lecture number 5, and in this lecture what we are going to look at a few more examples of reconstruction, but namely some complex reconstruction. So, this is of course much more time consuming to understand it clearly, but I would like to show you a few examples how complex the reconstruction can be on surfaces, and then we will familiarize today hexagonal lattice, and in the hexagonal lattice the surfaces are represented by something called Miller-Bravais indices and not just with Miller indices. Of course, you can also represent it with Miller index, but Miller-Bravais lattice is a more common practice, and we will also finally conclude with the two-dimensional Bravais lattice, because that is what is very important for us. As you have seen in the three-dimensional Bravais lattice, we had 14 different group, and then here we are going to just have like 5 indeed. Alright. So, let us have a look at the silicon 111 surface. So, this is again a type of bulk crystal, and this what you are seeing is actually the idealized silicon 111 surface, or what you would expect to see basically. So, the light blue atoms are the one on the top layer, and the one with the dark blue is basically the one just in the second layer. So, that makes it, although it looks like a hexagon, the symmetry of the surface is threefold and not sixfold as in the FCC 111 surface. Well, now that is the key, but this is what is expected. But the interesting thing is, when you look at the surface in reality, this is what you actually just end up. This you have like an extremely complex reconstruction on the surface. Well, it is hard to first understand, but let me try out to make you understand this. So, what you have to follow is this red line here, that is actually the unit cell which is being converted finally to the reconstruction, and that is why finally it is known as a 7×7 reconstruction, because the periodicity after the reconstruction is basically 7 times of the original unit lattice vector of the silicon 111 surface in an ideal case. Now, what you notice here is that particularly in the side view, what you realize is that there are these yellow atoms which are actually known as the add atoms, or add atom. In this case it is actually said because it is looking like kind of an atom which is adsorbed on the surface, but ideally this is nothing but the silicon atom. This is actually in the topmost layer, but look here, in this case, the ideal case, the number of top layer atoms was actually about 43. You can basically count it, including the one in the corner and at the edge, it is about 43 atoms. And now, after the reconstruction, the number of atoms on the top layer is actually now reduced to just 12 on the top layer. This is quite interesting. Now, you understand the philosophy behind the reconstruction of the surface, that the surface actually reconstructed in a way that the total number of surface atom is actually reduced almost by, you can see, about 1/4 of the original. So, this is quite striking, that finally the number of surface atoms are actually reduced, and the advantage now, if you look at the second layer, which is basically represented by this light color, and those ones you can see they all get more coordinations now. You can see all of them are getting much more coordination that you would have actually expected in the normal case. So, that is the whole point here, and at the same time the spacing between the atoms are also changing compared to the ideal case. Then you also see something called as dimers, which are actually particular atoms that are also seen in between. So, that at the end of the day what you are seeing here is actually the surface is organized in such a way that the top layer atom number is reduced, and every other atom which is below in the second layer is actually getting a higher coordination. So, that is the philosophy basically, that then effectively the total surface area or surface energy is basically reduced in this case compared to the silicon. So, this is known as a silicon 7×7 reconstruction, and it took about 20 years for the surface science to completely solve this, or it was a long unsolvable problem for about 20 to 25 years, and then with the discovery of scanning tunneling microscope people solved it. We will come to that story a little later. And now if you look at the scanning tunneling micrograph, that means topography, you see basically again this oblique here. This is exactly the same as the one which is represented here in red. So, I am just going to use a different color here, just so that you can visualize it better. And now if you count all the bright atoms inside, I am sorry for that, all the bright atoms inside, you can see here that there are 12 bright atoms that are inside the cell. So, that is again 12 atoms, and the 12 atom is exactly what we have just said in this case, that is the top layer atom. So, what you are seeing in the STM image is a 12 surface atoms, and the unit cell you can see it looks very different compared to what you would have expected for the ideal case. So, this is an extremely complex reconstruction. So, the reconstruction can be as complex as this one. That is what I wanted to show you. You can see more details in this reference. Now, let me show you another example, which is a gold 111 surface. So, this is the gold 111 surface you would have expected, right, a hexagon, a perfect arrangement of the atoms, but that is not what you observe in reality in STM image. So, this is again an STM image. Basically there you see that these are the surface atoms, that they actually just form some kind of a herringbone reconstruction. So, this is known as a herringbone reconstruction. So, what is going on inside is quite interesting, that the reconstruction go over a very large number of atoms of about 23 times of the original unit cell, and during this journey you can see the original atoms are actually getting displaced at the position. It comes to something called an FCC region, then it go through a bridge region, again an HCP region, then a bridge region, and finally again to FCC region. So, what causes this one causes basically kind of ripple on the surface. So, that means some of the atoms are slightly higher and some of the atoms are lower, then again higher, and so on. So, you can see these region which is represented are high, they are actually high in the topography, and then these region are basically low in topography. So, that actually makes the corrugations looks like up and down, and this is exactly what you are seeing in the STM image, that some regions are appearing brighter and some region are actually just appearing darker. Yeah, so, we can represent the darker region with a black color. So, this is actually appearing as darker region and these regions are appearing as red. So, this is basically due to the fact that the atoms are actually corrugating on the surface. But now you see the reconstruction is actually about 22 times root 3. It is a very large reconstruction. That means the surface atoms are not just reorganizing just with its neighbor, but it is actually reorganizing together with about 23 atoms along a unit lattice direction. So, this is extremely complex, and this I have actually just brought to here is just to show you the different type of regions which I have used here, called the hexagonal close packing region and the face centered close packing region, where the packing is basically in like an AB type, and in the CCP it is basically an ABC type, and that is what the FCC region and the HCP region basically meaning. Yeah. So, just keep a look. You can try to look that in greater detail. So, just for your understanding, the circles are actually representing the top atom and the dots are representing the atoms below, and the hexagon is basically to just guide you through the symmetry of the surface. Now, let us have a look at some special surfaces. So, the graphite surface, because we are also going to look at a few examples later where you will be using graphite. Well, graphite is also nowadays quite interesting after the discovery of graphene, because graphene is nothing but just a single layer of graphite. So, graphite comes under this hexagonal bravais lattice. Here the yellow atoms are actually the top layer and the gray atoms are actually the second layer. So, what you are seeing here in this image is the arrangement of the atoms. So, the atoms are basically arranging in a hexagonal manner and they form the top layer and the bottom layer are slightly just shifted with respect to each other, that is making the two different type of atoms on the graphite layer. One is known as a B site and another one is known as an A site. What is an A site? A site is actually having the carbon atom with a neighbor in the second layer, and B site is the one which is having no neighbor in the second layer. So, that is basically the A and the B site. Now, if you look at the STM topograph, so that is again the micrograph with which you can actually just get the atomic resolution, where the bright so you can see basically that the whole thing is going like a hexagonal lattice. So, the bright lines, if you connect, you can see I can form a hexagon with something in the middle. Now, when you look at the graphite itself, it is not very clear why we should see basically like a hexagonal lattice in this, because you can see like much more atoms, or it is more like a honeycomb type of pattern rather you see in this case. So, what is the reason for that? Now, if I would connect basically the A type atoms together and the B types atoms together, then you would find that, well, I can actually just draw two hexagons easily on the surface. Now, the interesting thing is that in the STM topograph, what we are seeing, or the bright dots, are only the B site atoms. The atoms at the B sites are the one we see in the STM topograph. That means, these are the atoms that we are seeing. So, now you can see, I can see all these bright atoms, yeah, these are the bright atoms, and the one in the middle is again the bright atom. So, that is why when you look at the hexagon, I can see 6 bright dots, and in the center also I can see another bright dot, right. But now, the atoms which are actually these ones, which are the B site atoms. So, let me just represent it using a different color. So, these are the B site, sorry, the A site atoms. They are appearing rather weak in the contrast here, you can see. So, they appear in the contrast, but they are rather weak compared to the atoms at the B sites. The reason is very simple. The atoms in the B site having no neighbor in the second layer, therefore, they are much more visible in the STM than the one in the A site. So, that is the typical surface, and now what I would like to discuss with you is how you would basically name the lattices or the planes on this kind of surfaces like hexagons, for example, hexagonal lattice. So, this is the unit cell, and now let us do this for a hexagonal lattice. So, the difference of the representation of the hexagonal lattice compared to the one we have seen before is that here we use 4 indexes and not 3 like HKL. We use an additional index, namely I, and I should follow this particular rule, which should be basically a minus of H and K, H plus K. So, this typical representation is known as Miller-Bravais indices, and this is basically represented using 4 different indexes. So, where are the 4 different indexes coming from? In the HKL, you were familiarized that the HKL coming from the X, Y and Z directions. In this case, it is not really so. This is basically represented by A1, A2 and A3. These are the 3, that is the HK and I, and the L is basically representing the direction which is perpendicular to all these A1, A2 and A3. So, that is how you can basically represent the entire cell, entire unit cell of hexagon. Now, if I would represent like this, and if I want to basically just create a plane inside this. Now, let us assume that I want to create a plane like this in the hexagonal lattice. Now, what I all need to do is I need to look at the time at the intercepts of this plane along the different unit lattice direction. So, you can see along A1 I have one intercept, along A2 I also have one intercept, but now the interesting thing is along A3, this is the A3 direction, but it is minus A3, the negative direction of A3, and you can see this is been cut 2 times. So, that means the intercept along A3 is basically, so this is A1, this is A2, this is A3, it is basically minus half. And then along the other direction, which is the z direction, so there you can see the intercept is actually infinity. So now if you take the reciprocal of that, then I get the plane. So you have 1 1, and this is actually represented as bar 2. So typically when you want to represent negative in indexes, so you would call it as bar and then 0. So this is the plane. So the particular plane that you are seeing, it's actually 1 1 bar 2 0. Now let us visualize how this looks like in the hexagonal lattice. So this is the hexagonal lattice, where you can see this is my A1, this is A2, and this is A3, this is A3, and this direction would be the z direction. And now you can see how the plane is represented in the hexagon, and this is actually nothing but the 1 1 bar 2 0 plane. Yeah, so this is the way you basically index the surface. Now let us have a look at a couple of more examples. So like the Miller index again for a different hexagonal lattice. So this is the two different planes that I would just like to represent. You can first of all look at the intercepts, and from there you can calculate the or understand or represent the Miller bravais lattice. And this plane is nothing but 0 1 bar 1 0, and this one is actually 1 bar 1 0 0. So the planes are actually the similar type. It is just facing the different sides of the hexagon, and of course if you look in the crystallographic plane, they are actually oriented in a different direction. So therefore they have different name. But once you create a plane out of that, it is actually unimportant from which plane you have actually just cut. So all the different type of planes that comes under the similar family is going to actually just give you out the same type of surface. Now if you look at that surface, so this is basically the surface, and that surface is nothing but 0 1 bar 1 0. Yeah. You can actually create as many surfaces as you want. Please do it as a couple of exercises. You can try to understand and create different type of planes using the Miller bravais lattice for the hexagonal lattice. Now the most important plane in the hexagonal lattices are actually not the one we have seen. It is actually this particular plane, where it is parallel to all the A1, A2 and A3, and it only basically just intercept the z axis. Yeah, and that particular plane is therefore known as the 0 0 0 1 plane, or the Bessel plane of graphite surface, or even for other hexagonal type of surfaces, this is known as a Bessel plane. Yeah, so this is how the surface looks like, and this is the lattice directions, and this is typically what you would find in the case of the graphite. That is also the reason why you can represent it like that. And now I can actually just cleave the surface along the Bessel plane that is very commonly observed in hexagonal lattices. For example, graphite, if you take and you cleave a couple of layers out of the graphite, you can basically just generate graphene, for example. Yeah, so that graphene is actually coming along the Bessel plane, or one of the Bessel plane is the graphene itself. Therefore the Bessel planes are actually very important in the case of graphite. Now there are also a couple of other examples about hexagonal lattice. For example, the most famous ones are the metal dichalcogenide, tungsten disulfide as an example. There also you can see the whole thing is actually just looking like a hexagon, where the adjacent layers are basically just displaced by a given atom, and that looks like exactly what we have seen in the case of graphite. But now the interesting thing when it comes to the graphite and also the tungsten disulfide, the adjacent layers are basically like interacting through a very weak interaction, namely the van der Waals forces. Yeah, so the layers are actually held together by weak interaction, like van der Waals interaction, and that is also the reason why these materials are much more easy to cleave along the basal plane, and cutting them through other planes are extremely difficult. So therefore you would not find in the market a hexagonal or a graphite, for example, which is plenty available is always the 0, 0, 1 surface, and you would not find, for example, other complicated or other more complex planes are not really readily available because they are more difficult to obtain. Yeah, but 0, 0, 0, 1 planes are easily available in the market for purchasing. Well, now I come to the final slide of the lecture. So, this actually just summarize the two-dimensional bravais lattice, and in the two-dimensional bravais lattice we have basically 5 different point groups. Yeah. So, these ones are typically represented, the first one is oblique, where the unit lattice vectors A and B are not equal and gamma is also not equal to 90 degrees. So, that is basically is the oblique lattice, or most of the lattices you can basically put it in the oblique. And now, if you would basically keep the gamma to be 90 degree and keeping the A and B not equal to each other, then you can actually just form the rectangular unit cell, and then you can actually just by keeping the gamma 120 and A is equal to B, you would get nothing but the hexagonal lattice. Yeah. So, that is the classification. And now, the rectangular unit cell, you can actually just create 2 different type out of that, where you are keeping the gamma at 90 degree same as in the rectangular, but now A is equal to B, then you would come to something like the square lattice. Now, out of this there is actually a very special group that is called as the centered group, where you have the same classification or the same characteristics as in the rectangular one, but the only difference here is that you have basically something at the center of this rectangular unit cell. So, now you can see that the entire different possible surface is actually like surfaces can be classified into these 5 different point groups, for example. Now, the point group of these different things can also be just looked. This is actually called as P2, this is called as P2 mm, this is called as P6 mm, this is called as P4 mm, and the last one is actually the centered one rectangle is actually known as the C2 mm, where P represent primitive, that means it is a primitive cell, it has only one atom in the cell, and C represent basically that it is a centered cell, and 2 is basically representing that it has a 2-fold symmetry, and 6 is representing, for example, it has 6-fold symmetry, and 4 is representing that it has 4-fold symmetry. Yeah. So, the number basically representing the symmetry of the surface, and the P or C is basically representing whether it is a primitive or centered, and the last one M and M are representing whether there is actually a mirror plane or not. Well, you can see here for the rectangle I have a mirror plane along this direction and I have a mirror plane along this. Yeah. And also the same for the hexagon. So, I have a mirror plane along this and I have a mirror plane along this, and here also I have 2 mirror planes as you see here, and that is why they all have like 2 mirror planes, that is what is represented by the 2 different M's. Well, that is a summary of the bravais lattice, and as I have already told you, we can classify all the different type of lattices that you observe in surface can actually be classified into any of this, and for example, our 110 surface should be corresponding to the rectangle or P2 mm, and the 100 surface can actually be put in the P4 mm to square, and for the 110 of the BCC can actually be represented by C2 mm, for example, or the hexagon can actually be represented by P6 mm and so on. So, with this you can classify all the surfaces, and you can either represent the surface using the symmetry, or you can actually also represent by the plane itself, which we have already learned in the previous classes. What I wanted to also just summarize here is that these different type of surfaces are now commercially available and you can purchase them in the way you want, and to maintain their cleanness and also to maintain the stability of the surfaces, ultra high vacuum technology is very important. And therefore, next week, before we go into understanding more about the surfaces, I am going to introduce to you to ultra high vacuum technology, which is actually one of the major development that has actually just created the surface science into the current status. Yeah, and also where people could understand things at an atomic and molecular level. So, with this I would like to conclude this lecture, and I will see you in the next lecture. Thank you very much.